Everyone. I'm still super sick, so if I sound sick and whatever, sorry about that, but gonna have to make do. So we've got what's hopefully gonna be our last lesson online for the moment, although it's period 3, so for you right now probably, so the news has perhaps been announced. I don't know. It's the perks of you living in the future compared to me when I'm recording this video. Anyway, so we've got today's lesson, which is on impulse. It's going to be something that's not too tricky once you get your head around it, because it's just building on stuff we've done already. So all you need to know to start with is impulse is the change in an object's momentum. So it's a word that we don't just call change in momentum, we just give it that special name, impulse. So the impulse is just the final momentum of an object. Take away its initial momentum. We show impulse with a big capital letter I. So the impulse is equal to momentum final, PF, take away momentum initial, PI. Now, impulse, it's a vector quantity, and we need a direction as well as a magnitude. So an impulse, it's kind of like momentum. It's got a number saying how strong it is, and it's also got a direction saying in what direction the impulse is. It'll make more sense with an example. Just remember, it doesn't say up there right or yet, but momentum, it's just the mass times the velocity. It's a vector quantity. Impulse, pretty much the same. So the example is, you've got a car, like my cars in all my examples, it's got a mass of 1,000 kilograms. It's moving east at a speed of 10 meters per second. It then increases its speed to 20 meters per second. What is the impulse of the car? So we find the impulse by finding the change in the momentum. We find the final momentum. We subtract the initial momentum. It's got a mass of 1,000 and its final speed is 20. So 1,000 times 20 gets me the final momentum. 1,000 times 10 gets me the initial momentum. The difference between those comes out to 10,000 kilogram meters per second east. It was moving east. It's still moving east. And so, yeah, its momentum is, its impulse is going to be in the east direction. So if the answer had come out positive, which it did, it would be in the east direction. If the answer had come out negative, it would be in the west direction. So you think about which direction is positive, which direction is negative, and that's going to help you figure out which direction the impulse is in. It's got units of kilogram meters per second, exactly the same as momentum has. So it's a change in momentum. It makes sense it would have the same units that momentum has. Since the answer came out positive and east is positive, the impulse is also east, like I just said. So another example helps illustrate the point. Same car, mass 1,000 kilograms, moving east at the same initial speed as before, 10 meters per second. It then decreases its speed to 5 meters per second. What is the impulse of the car? Same steps. Impulse is the change in momentum, final momentum, take away initial momentum. Here we've got 1,000 times 5. The speed at the end is 5. That's the only thing that's different here. And if we do that calculation, we get out minus 5,000 kilogram meters per second, which, like I was saying before, since it's a negative answer, it's going to be in the west direction. Since east was positive, west would be negative. So it's important that if you look at the first answer, it's got minus 5,000. If you look at the second one, it's just positive 5,000 west. If I'd said minus 5,000 west, well, it's like, if I've got the minus, that suggests the other direction will be positive, so that suggests it's east. Just make sure when you write your answer, you've got a positive number and a direction. Don't go putting negative numbers with directions. If you just had minus 5,000, like in the first one, that probably wouldn't get you a mark because, well, east is the positive direction, so you'd need to specify west as the direction. In that case, a minus in your answer probably isn't going to cut it. Just what I was saying. So we can think of impulse as being the change in the momentum. We can also think of impulse as the force exerted during a collision and the time over which it occurs. And the equation for that is that impulse is equal to the force on an object multiplied by the time over which that force is being exerted. So, yeah. We've got all our units there. Force has standard units of newtons. Time has standard units of seconds. We use a delta t in the equation to show the time, but really you could just use a t to show time. I'm just putting the delta there because it's kind of standard notation. That's what you will see. But if I just said F times t, that would have been just as good. It's the force acting over a certain time that determines the impulse on the object, its change in momentum. So, quick example. you've got a bat, it hits a ball with a force of 100 newtons. The collision takes place over the course of 0.1 seconds. What is the impulse on the ball? It's a simple calculation question. We've got an impulse equal to force times time. Force is 100 newtons, time is 0.1 seconds. Multiply them together and get out 10 kilogram meters per second. There's no directions given in the question, so if the force is 100 newtons, it's in a positive direction because it's a positive number. The impulse is in the same direction, so it's a positive number as well. That's as much information as you can give in terms of direction there. If the force had been a negative number, the impulse would have been negative, and that would have told you your direction in that case. But we do the best that we can with the information that we're given. Without a direction in the question, we can't really give a word direction in the answer. Now, carrying on with that idea, so if you've got a graph which has force on the vertical axis and time on the horizontal axis, and you find the area underneath that graph over that time period, that's going to equal the impulse on the object. So the area underneath that shape gets you your impulse, the change in momentum. And I'll go through an example of exactly how that works. So you've got a graph here. If you check the axes, it's got force in newtons on the vertical and time in seconds on the horizontal. When you do a question like this, it's important to always read the units on the axes. If it's newtons and seconds, then everything's good, but you might have kilonewtons on the vertical scale, for example, or milliseconds on the horizontal scale, and if that's the case, you'll have to adjust by, well, a kilonewton is 1,000 newtons, so you'd have to times your answer by 1,000. If it was milliseconds, well, a millisecond is 1,000th of a second, so you have to divide by 1,000. You've got to adjust based off what your scale is. I see how people go, but it's one thing you've got to kind of keep an eye out for when you do these sorts of questions. So the example is the graph below shows the force on an object over time. Use the graph to find the impulse of the object. So impulse is the area underneath the graph. There are two methods for going about this. One is smart to use here. The first method I'll show you is useful here, but the second one is more general and can be used for shapes that aren't so nice. I'll go through that in the next slide. So to get the area under the graph, well, we've got two parts. We've got a rectangle that is 2 tall and 3 wide. The area of that rectangle, 2 times 3, is going to be 6 kilogram meters per second. We've got a triangle, it's 2 tall, it's 2 along the base, it starts at 3, it ends at 5, so it's 2 along the base, area of a triangle, times the base and the height, and then divide by 2, gets you out 2 kilogram meters per second. So the total area under the graph is just going to be those two things summed together. 6 plus 2 gets me a total of 8 kilogram meters per second. So find the area under the graph by breaking up the graph into simple shapes. That's just the easiest way to go about with doing it with a question like that. Now, method 2, for the same graph, it's less applicable here because you've got a nice rectangle and a nice triangle shape, but this is going to be something you're going to need to be good at in Year 12 physics, so we'll use this as a chance to practice it. We do this in 3 steps. First step is find the area of one small square. Then we multiply this by the number of squares underneath the graph, and that's going to be the total area under the graph. So we find the area of one square, we count the number of small squares, we times those together, that gets us our area. So I'll go through how this would work here. So one of those small bluish squares, if you look along the horizontal, it's easy to see that it's 0.5 wide. On the vertical, it's going to be, well, there's 3 squares across a distance of 1. So if I go up from 0 to 1, that's 3 squares. Each square would just be a third tall. I'm just going to approximate that as 0.33. So each square, it's 0.33 tall, it's 0.5 wide. The area of one square would be those two things times together, 0.167, again, just an approximation. Now, I've gone ahead and counted the number of squares under this graph. That might seem silly because there's a lot of squares, but sometimes you won't have a simple rectangle and simple triangle. You might have some shapes where you can't get the area, and in that case, you do need to count squares. A general rule that we have in physics is that if you've got, say, well, you've got whole squares for some parts, but sometimes if you look under the triangle, you've got like half squares, sort of not fully under them. There's one up the top near where the triangle begins, where you can see it's kind of under the graph but not fully. A rule that we have is that if something is half a square or more, you count it as a full square. If something is less than half a square, you don't count it at all. So it's easy for me to point to this, and if we get time, I remember, like when we do this down the track in future areas of study, I can show you then. But it's a good rule to keep in mind that if you're counting squares, you don't have to try and combine them together in order to make a full square to be as exact as possible. There's a bit of leniency in your square counting if like you think there's 48 and I think there's 47 or something like that. But the rule that we tend to follow is half a square or more counts as a full square. If it's not half square, don't count at all. It tends to balance out that way and helps us get like a good answer. Anyway, that's on a heap of stuff about counting squares. So 48 squares, each one's got an area of 0.167. We multiply those two things together, and what do you know? We get the exact same answer, 8 kilogram meters per second. So same answer as we'd expect, different method. It's not as applicable here, but it will be down the track, so we're taking a bit of time to see it now. Now, talk a bit about seatbelts. So you should wear seatbelts. Please keep that in mind as just a general life rule. The use of seatbelts illustrates the relationship between impulse and force. So you got a car hitting a tree. Yeah, that's a decent picture. I thought it was objectionable, but whatever. So the example is a person of mass 80 kilograms is driving at a speed of 30 meters per second, then hits a tree and comes to rest. I think that's a nice way of saying he died. Calculate the force acting on the person. A, if they have no seatbelt and stop during a time of 0.01 seconds. B, if they have a seatbelt and stop during a time of 0.2 seconds. Now, the mass of the car doesn't matter here for any of these calculations. Keep that in mind. I'm talking about the impulse on the person, the force on the person. If I had said how much the mass of the car was, I wouldn't have needed it at all to get my answer. It's just a case of you only need the mass of a person for a question like this. The mass of everything else is just extraneous and there to throw you off. So you can see with the seatbelt on, the person takes longer to come to a stop. That would probably be sensible to you. The seatbelt kind of exerts a force against you and slows your stop. And we're going to look at exactly what that does in terms of the impulse and the force on the person. So, question A, they have no seatbelt, they stop during a time of 0.01 seconds. So what we're interested in is calculating the force on the person, and that's what we're going to do. Force is impulse divided by time from our earlier equation. Impulse is change in momentum, so we'll approach that first. Change in momentum, final momentum, take away initial momentum. Final momentum is mass times final velocity. Initial momentum is mass times initial velocity. The final velocity is 0. The initial velocity is 30. We do a calculation and we get out negative 2,400 kilogram meters per second. So that's our change in that's our impulse, our change in momentum. Now we can use that in that top equation, F equals I divided by T. So the force is the impulse of 2,400 divided by 0.01, my time that I'm stopping over, gets me out a force of 240,000 newtons. I'm ignoring the minus sign. I shouldn't, don't know why I did. I guess the idea is just that the number itself is the quantity of interest here, but I probably should have said that the force is a negative in this case. It's kind of my bad that I didn't, but it's the size of the number that kind of matters. So for question B, you've got the same seatbelt, same person, same setup, and they stop during a time of 0.2 seconds instead. So I'm going to go through and do exactly the same thing that I just did. They're stopping over a longer time. The time value is different, but everything else is exactly the same. The impulse is exactly the same change in momentum, same final speed and initial speed, so nothing's different here. When I do my calculation with a different time value, I've got a time value of 0.2 rather than 0.01, and that gets me out 120,000 newtons. So the impulse is the same in both cases. I can't read because the video is covering up the bottom of this, so I have to move it around. So that won't make sense when I've actually moved it. However, because the seatbelt greatly extends the time at which the person stops, it greatly reduces the force on the person as they come to rest. So that's what the seatbelt is basically doing. It's slowing the person's stop down, so they're stopping over a greater period of time. That leads to a smaller force being exerted on them. Here it's 12,000 newtons. Before it was 20 times bigger, 240,000 newtons. So you've got a smaller force being exerted on the person, and obviously, like, they might leave with a broken nose or something rather than, you know, actually dying in a case like this. So it takes a smaller force to stop them over that longer time period. You don't need a sudden harsh force in order to stop them, and so it's more likely the person is going to live. Similar case, I didn't include a slide on this, probably should have. Like if someone jumps off a building, these are all very unpleasant scenarios, but they make the point. If they land on concrete, they stop straight away. So a very small time frame over which they're stopping means a very large force on them that would kill them. If they jumped off a building onto a trampoline, the trampoline would compress, and so they'd stop over a longer time period. Because that time period is longer, there's a smaller force and they're more likely to be okay. Please don't jump off a building onto a trampoline in order to test this, because I think you actually do kind of, if the building's big, you end up dying anyway. So yeah, be careful is the point. So it's just basically illustrating the same idea. You change the time over which someone is coming to a halt because of a seatbelt or because they're jumping onto a trampoline. That reduces the force that is going to lead to them being a bit better off. And that's it for today's lesson. Just make sure you're doing those textbook questions first of all, and that you're trying the checkpoints questions as well.